We go.
All right.
So today we're going to talk about PET quantitation and quality control. So let's start by defining what we mean. So when we look at PET images, we could do a visual assessment, what's known as a qualitative analysis. And that may be adequate for some tasks like diagnosis or staging. But we know that quantitative measurements are more accurate. They're certainly less observer-dependent measures. And it is particularly important to have quantitative accuracy and precision when you're trying to combine data from, it could be multiple patients, it could be the same patient done on multiple pieces of equipment, or it could be multiple sites in, say, a clinical trial. We know that it's not easy to achieve this, but the reward is that if you, the more you can move towards being quantitatively accurate and precise, the earlier that, for instance, in oncology, that you can identify those people who are, say, responding to treatment versus those who are not. And in clinical trials, if you have better statistical and clinical significance, you may be able to get the answer with fewer scans. So how do we go about this? So our goal is that the PET image, after we've reconstructed it, that when we look at a particular voxel, that intensity will be directly proportional to the amount of activity that's in the patient. But in order to do that, we're going to have to develop a set of corrections to compensate for the fact that we don't have a perfect detection system. There are nonlinearities, there's non-uniformities, and we also have to account for the effects that occur within the patient, like the scattering and attenuation of photons. So we have a ring of detectors in our PET scanner, and each of the detectors is receiving light from the annihilation of positrons of electrons. So we have this series of oppositely directed 511 keV photons. And what we want to do in the ideal is to detect both of those photons, because then we know, we get information about where along that line that connects those two detectors this event happened. So we have detector A here, and as the light from the patient comes into the detector system and generates a signal, there's some threshold at which point we say, that's an event, I need to look at that. And so I get a little, like, my system will generate a little blip saying, okay, I have an event. So now you're going to look to see if there's another event corresponding to the other photon that went in the opposite direction. So say it ended up in detector B, it has a similar sort of threshold. So now we're going to look in the window between when the first event happened to see whether there were events in other of the detectors which could be potential coincidence events. So we need to make this window wide enough to account for the amount of time that it takes for the photon to travel from one end of our field of view, which is on order, the transaxial is about 80 centimeters. So at the speed of light, how long would it take for the photon to reach the detector? And then we also have to account for the fact that there can be some additional delays as the signal goes through the electronics and is interpreted. So what we look here at our ring detector, and we look at two detectors. What we were hoping to measure are these, what were called true coincidences, where there was an annihilation event, we had two oppositely directed photons, and both of them ended up being detected. Unfortunately, that's not all that we measure, though. Each of these detectors receives photons from other events. So as these photons travel through the patient, some of them will interact with the matter in the patient. So we have light interacting with matter. And the primary interaction is Compton scatter. So in green here, we see one of those where this photon was leaving this particular position, and somewhere along the way, it underwent Compton scatter. And the result is that the photon gets deflected into a new direction, and it loses some of its energy. So we may very well interpret that to be a true coincidence, because we don't know that this change in direction happened. So the problem with scatter is that it reduces the contrast in our image, because we end up mispositioning where the event happened. We'll think it happened somewhere along this red line, when in fact it came from this green line. The other problem we have to deal with is random coincidences, where we have completely unrelated parts within the patient which generate photons, and they happen to strike the two detectors in that little coincidence timing window that we set. So what we actually measure is a combination of all of these. So we have the trues reduced by the effect of attenuation, we have the scatters, we have the randoms. So how are we going to get back to what we want, which is the trues? Well, we're going to have to apply a lot of corrections. And I've listed the ones which are most normally applied. There's attenuation, scatter, randoms. There's a dose calibrator, cross-calibration with the scanner, linearity and distortion correction, energy, normalization, and dead time. We don't have time to go into each of those, so I'm going to concentrate on those first four. So let's talk about how we can compensate for attenuation. So if we look at this diagram here, we're looking at, say, the chest of a patient, and we have events which are generated in the patient, and the oppositely directed photons reach our detector. The flux that we're going to measure at the detector is going to be reduced because by attenuation. So if we went distance d1, this photon going this direction traveled through a distance d1, then the number of photons which actually make it out to our detector is reduced by this factor mu, which is the linear attenuation coefficient. And that varies with the density of the material that the photon is traveling through, and also the energy of that photon. But it's not sufficient for one of our photons to make it. We need that pair of photons to make it. So actually, the overall reduction in the pair of photons is both factors, the factor for going in distance 1 and the factor from going in distance 2. So you can add those up, and actually what we need to know is simply the value for the entire distance through the patient, because those photons have to travel in both directions in order to reach the detector and be a coincidence event. So how can we measure this factor so that we can apply it? Well, we can do it by doing a transmission. So since we need to measure what makes it through the entire width of the patient, we can put a source outside of one end of the patient and just measure what makes it through to the other side of the patient. And from that, by taking a ratio of that to the same, what you get when the patient is not in the field of view, we get a set of corrections, a map of attenuation coefficients. So in older scanners, this information, the transmission information, was generated using a single photon source whose energy was sufficiently different from the 511 that we could distinguish it from what was coming out from the patient. And so you would get a map which looks something like this. And this would be applied during the reconstruction. In more modern scanners, we've moved away from that, and now we're doing the attenuation measurement using a CT. And just to show you a comparison, here's an image with and without attenuation correction. And in fact, this correction for attenuation is the largest correction to the data that we need to make. One of the upsides of using a CT to measure the attenuation is that it's really fast compared to rotating a source around the patient. A complication, though, is when you just are using a single energy source for your transmission, it's a simple scaling to adjust what you measured down to the actual attenuation that the 511 keV photons would experience. If instead you're using an X-ray source, those are not monochromatic. They have a range of energies, and therefore there's going to be a little bit of error. We're going to choose an effective energy kind of in the middle, and that's what the scale factor that we'll use in order to scale it up to 511. These lower energy photons are going to experience more attenuation than our 511s are, because they're less energetic, and therefore we need to compensate for the difference in the two energies. We also have to downsample the CT image so that the resolution matches that of PET, and in order to avoid ringing artifacts. And we also have a problem that at lower energies, there's more of a difference in bone versus tissue than there is at higher coefficients. So there can be error in scaling from the different materials. So that's attenuation correction. Any questions? Okay. So now let's talk a little bit about scatter. All of the systems that we're using are fully three-dimensional scanners. So some of the earlier scanners used septa to try to discriminate against those less desired photons, the ones that arise from scatter and the ones that arrive from random coincidences. So by requiring that the photons be emitted in more or less perpendicular to the patient directions, some of those are yet screened out by these septa. So we don't have as large a fraction of those events in the data. The problem, though, is the cost is that some perfectly valid true coincidences are going to be screened out by those septa too. So it's a mechanical rejection, which does succeed in getting rid of scatter and randoms, but at the cost of sensitivity of your system. So if we get rid of those septa and just open up the entire surface of the detector, then the penalty is that we're going to have a much larger fraction. In fact, scatter fractions on the order of 30% or more are quite common. So how can we discriminate against this scatter? Well, one way we can do it is by setting a limit on the lower end of the energy window. So if we have a system which has an energy resolution which looks something like this, around 511, we can go to the end of that distribution and say, we know that anything which is below this value is scatter. It's not true. So I just won't even bother to record those. I'll reject them right out of hand. If I have a system which has better energy resolution, so it has a narrower distribution, I can move that limit up higher. And so I can eliminate a lot of this scatter, and now I only have to contend with the part that overlaps with the trues. So now I need to find some way to correct for that. And the method which we're using is a modeling method. So it's called single scatter simulation, where you look at a pair of detectors, you choose random positions within these so-called arbitrary scatter points, and you apply Klein-Nishina equation and the solid angle from these various locations, and you come up with the result that then has to be scaled in order to deal with the fact we're only modeling single scatter. There are multiple scatters and additional other factors. So scaling can be accomplished by a couple of different ways, and different of our systems apply different methods. One way is to do tail fitting. So we know that if we look at the boundary of the patient, any accounts that we see outside of that must be scatter, because there's no activity out there. So we can adjust so that the estimate matches those tails in the distribution. So the downside of doing it this way is that the boundary of the patient is determined from the CT. So if the patient moves between the CT and the PET, then that will throw off this calculation. And the other problem with it is that if you have a very large patient who fills the entire field of view, then you're not going to have tails on the side. It's going to be person all the way out towards the detector, or you're going to have a very low count, noisy tail. So a different way of doing it has been introduced in some of our newer scanners, where instead of using tail fitting, they actually come up with a scaling factor based on a small Monte Carlo simulation. And I've given you the reference for this method of scatter correction. So now moving on to randoms correction. What can we do to measure the randoms correction? Well, we can go back to our original idea where we had signal A and signal B from our two detectors. And we know that a true coincidence is going to happen within the time it takes for those photons to reach the two sides of your detector ring. So instead of using a coincidence window here, what we're going to do is we're going to collect another set of data where we're going to introduce a big delay in this window so that by a time that's much longer than its width. So for example, we're not going to look in those first couple of 5, 9 to 6 nanoseconds. Instead, we're going to look way out, maybe 60 to 66 nanoseconds. So anything that the coincidence circuitry then says, oh, this is a coincidence, can't possibly be a true event. So instead, it's a measure of your randoms. So we'll take these events, we'll sort them into sinograms, smooth it, and apply that during the reconstruction to compensate for their presence of randoms. Questions? Anyone? Okay. A very important calibration is also required in order to do quantitation, and that's between the dose calibrator, where we're going to measure the dose that goes into the patient, and the scanner. So we need to have an association between activity and the output from the system. So the way that we can do that is we'll take a dose, we'll measure it in that dose calibrator, we'll inject it into a uniform phantom with a known volume, we'll make sure it's well mixed so that we have a uniform concentration throughout, and then we'll scan that phantom on our scanner using the standard patient protocol, both the acquisition and the reconstruction. And then we can derive from that a global scaling factor. So as I mentioned, at one end of the approaches is a visual analysis. The next kind of degree of difficulty is to try to do something quantitative. If you use the standardized uptake value, people refer to that as being semi-quantitative, and we'll talk about that in a little bit more detail. But generally, you're applying that to a static view, which has been, at say, 60 minutes after injection for FDG. Now, in order to go to the next level of accuracy, you can do kinetic analysis, where then you're applying a pharmacokinetic model to the data that you've derived from a series of dynamics scans. One of the limitations of this system until recently was that you could only apply it to one position of the bed, and since the axial field of view of scanners is kind of in the range of 18 to 26 centimeters, that meant you needed to, that was the only fraction of the patient that you could do this analysis for. It also requires that you do a longer scan, and you also need to be able to do some sort of analysis of the input function as you inject this bolus of activity. And in order to do that, if you can't get something in the field of view that will give you the information from the image, then you're going to have to do arterial blood sampling, which is much more technically demanding. So one of the advantages of the new PET Explorer is that with that longer field of view, axial field of view, it's much easier. There's many more places within the patient where we can have, say, the heart in the field of view, the aorta or the carotids, so that the ability to generate an input function from the image is much enhanced. So let's talk about standardized uptake value. What
Could
is
I
it?
ask a really quick question, Janet? That just sounded so appealing. That means that the Explorer would actually, perhaps, the need for arterial sampling would be almost eliminated, right?
Correct.
In principle.
Yes.
That's so very appealing.
Yes.
It takes one of those other sort of how are things going to go in terms of the getting in the A line and doing all of that that is a pretty heroic multi-person event is removed. So just wanted to highlight that. That's just so very cool. Yeah.
Yes.
Rose, would you still need to measure metabolites though?
Well, I guess it depends.
Yes, yes, you would.
Yes, you would.
Yes, you would.
Okay.
Well,
Yeah.
so much for that.
Yeah. So something to consider. I mean, maybe there's some hybrid where you can get the better part of the or reduce the need for as frequent sampling, but you'll have to think that one through.
Could you get metabolites, and this is out of naivete, could you get metabolites with venous sampling rather than arterial so that you would basically at least not have to try to place an A line?
Yes, you could.
Yes.
So that would be helpful. Even that would be helpful. Right.
Exactly.
Okay.
Great. Okay, so back to SUVs. So what we're going to do with an SUV is we're going to take a ratio. We're going to calculate the activity in some particular region, and then we're going to divide that by the overall activity concentration in the whole patient. So here's the expression. So we're going to take the activity at the time of scan that's in a region, and we're going to normalize it basically by looking at the concentration if the patient were a uniform object. Basically, if we took that dose and you divided it by weight, which we're using as an analog for volume. So for instance, if we look at this example, we have a lesion within the patient, which, because we've done that dose calibrator cross-calibration, we can assign a kilobecquerel per milliliter value to. How hot is it compared to background? Well, that's what the SUV will tell you. And when we apply this factor, we get an answer for this particular lesion of, say, 1.8. So if you have a completely featureless, say, uniform volume where the concentration everywhere is the same as you do with a uniform phantom, then every part within it is going to have the same concentration of activity as every other part of it. So in that limiting case, your SUV is 1.0, basically, because the ratio, the concentration on the top and the concentration on the bottom are the same. So how can this calculation go wrong? Well, if you look, we need to know the dose in the patient. We need to know the patient's weight. We need to know the time of the scan. So basically, you could predict that errors in those are going to affect our SUV calculation. There are sites, in fact, that do not weigh the patients. They just ask them how much they weigh, or there are others where they just pull that information out of the patient record. And it could have been months ago, where for oncology patients, their weight can change quite a bit during treatment. So, and it could be that the technologist typing that information into the scanner did a typo. And another one that we find is that they will weigh the patient in pounds, but the scanner wants kilograms, and they make a mistake when they're doing that conversion. We also need to know we need the clock that's at the dose calibrator, where you're going to record the measurements of how much was in the syringe to start with, and then after you've injected, you're going to bring the syringe back and measure what was left. And each of those, it has a time associated with it. If those if that clock on the dose calibrator is different from what's on the scanner is going to base it on its own clock. And so you can end up with errors that are introduced by the fact that the times that you're entering into the scanner aren't scanner time, they're dose calibrator time. So you need to make sure that they're at the same time. And then, of course, another problem that we find is that the scanners don't help the technologists by doing the calculation for them, at least neither the Siemens nor the Philips. It requires that they know the net that was injected. So if they're not using a system like that will do the calculation for them, and like we have in our hot lab, then they could do an incorrect calculation so that the activity that they put into the scanner is incorrect, or they just make a mistake. So there's a lot of things that have to go right in order to achieve accurate information. We have to do this cross-calibration. We have to correct for effects in the patient. And also, this graph down in the bottom corner also indicates that the measurements that we make are dependent on other factors. They can be dependent on which regions we place, and they also can be affected by the size of that lesion and also by the reconstruction parameters that we apply. So I just wanted to include this information, so if you're interested in learning about a more exhaustive list of all the things that can affect quantitation in FDG PET in particular, here are some references that go through, and I really like this one by Ron Ballard that not only lists all of the different factors, but also gives you kind of approximate ranges of how much that particular factor affects the data. So there was a generational shift when time of flight imaging became a commercial product, and this was relatively recently. And the idea here is that instead of merely measuring where the pair of photons strikes, if in addition to that we can measure the difference in their arrival times, then instead of saying, oh, I got an event here, I got an event over there, it must have been somewhere along a line connecting them, I can say, well, because the fact that this photon got here this much sooner than this photon over there, then the location along there is restricted by some amount. It's not that entire line. And in fact, the precision with which I can measure the difference between the arrival times translates into the uncertainty that I now can place on where that event happened. So if you have a 500 picosecond ability to distinguish between the arrival times, that corresponds to now you can limit the location of that event to within 7.5 centimeters instead of the entire width of the patient. So having this additional information allows you to acquire a higher signal-to-noise ratio. In fact, the improvement is a factor of 2 times. And so you have better-looking images and higher contrast. Just to show you examples, here we have 2 non-time of flight, the same data then processed with time of flight, and you can see the improvement in the lower noise and the higher contrast that you get of lesions. So the first wave of time of flight scanners happened in around 2006, and each of the major manufacturers came up with a version of time of flight. We have the Philips Ingenuity, and this is our primary research scanner. We also have Siemens MCT scanners, both here and at our suburban locations, and then GE had their product as well, which I'm not familiar with. So the next generational change that came along was when the photomultiplier-based systems were replaced with a different photo sensor, and that's silicon photomultipliers. So again, you can now buy such a system from all the major manufacturers. The Philips Varios is going to be the replacement that we will receive for our Ingenuity. So we'll be replacing it with this system. And also bear in mind that the PET Explorer is based on the Varios silicon photomultiplier detectors. So we're already familiar with how that operates. We also have one of the Siemens Vision systems. And then, of course, there's also a GE product as well. So when we get a new system into our clinic, how can we compare across different manufacturers and across different models of camera? Well, there's a recipe book for that. It's called the NEMA NU2 standard, and it's basically got a set of instructions that says, follow this recipe, and you will generate a number which then can be compared. So if you have a NEMA number that was done on one system, and you have a NEMA number from another, you know that at least the same, you're comparing apples to apples. This standard has to be revised periodically in order to incorporate the latest capabilities. So there was a new version in order to include a NEMA measurement for time of flight resolution, for instance. And the current version has recipes for doing sensitivity measurements, spatial resolution, accuracy for count losses and randoms, accuracy for attenuation and scatter correction, and a measurement of scatter fraction, randoms, time of flight resolution, count losses. So I'm just going to show you some samples of this measurement. So in order to do it, you have this 70 centimeter long polyethylene cylinder. It has a hole drilled down it, and you put a line source of activity down there so it's an analog for a 70 centimeter long patient. So you have the scattering medium and activity. And then you take measurements over time as that activity decays. And from that, you can derive this sort of graph. So what we see here is a graph showing as the activity started at a high level and then gradually decayed, the fraction of events which were trues, those which were random coincidences, those which were scatter. And we can generate from that a metric called the noise equivalent counts. And you see that here in blue. So this is for our Philips Allegro system, which is multiple generations ago. It was a non-time of flight system. So what happens when we compare this information from 2 generations of PET-CT? So what you're seeing here on the left is our measurements for when we received our Biograph MCT, which is a 4-ring system. It's based on PMTs. And you see the same 3 graphs. And you see here the trues comes up, and then it reaches a point where the dead time and the pulse pileup actually results in a decrease in the number of trues that are recorded. The part that's shaded here indicates where we're operating in the clinical realm. So it's actually way down in this part. So that's generation before, and this is the new generation. So we have also, as I said, the SIPM base, and this is as much as possible, a comparison between the two of them. And we can see a couple of things which are quite different between these two. If we look here at the trues, we notice that it just keeps rising and rising and rising. So we don't have this problem with dead times out past where we can actually measure it. We've never actually found where the top of that is. We can see that the scatter fraction is here and the randoms are up here, and the maximum point along here where the NEC calculation occurs is much higher than it is for our MCT system. So, and it's much higher. So it's 181 kilocounts per second, which happens at this particular concentration. And in the new one, it's 300 almost kcps and at a higher activity level. So this is a side-by-side comparison of some of the things, some of the metrics for those two systems. In the red border now, I've put the new machine for comparison with the older machine. And we can see in particular this difference in sensitivity is nearly 50% higher. We can see that another quality is that the time of flight resolution, that ability to localize the difference between the arrival times, is much better in the new system compared to the old system. So does that mean then that we can't do quantitative comparisons among different models and makes of cameras? And the answer is no, it doesn't. And this is kind of an illustration that we can use to show that. What we have here is a Phantom that's intended to simulate the size of a brain. So in the lid, it has compartments that can be filled with activity. And then we also put activity in the background so that the ratio between actually there's 5 of these that you can't, is 2.6 compared to the background. So what we see here are the same Phantom that's been scanned on 2 different machines. This, one of our older scanners came into our clinic in 1998, and the Ingenuity, the current research scanner. So we have a system which has no time of flight capability. That on the left, it has a totally different crystal. It's GSO versus LYSO. It does its attenuation correction with the rotating source versus on the other one does it with CT. And yet, when we look at the results and we look at the target to background ratios, we see that they're actually quite comparable between the 2 different systems. So certainly the image quality is better. It's much more uniform compared to that, but the quantitative accuracy is similar. What we see here is the other part of that Phantom, which has cold rods down at the bottom with different spacings and sizes. So we see the sizes down here, and a comparison between scanning that Phantom on Ingenuity and then scanning it on the new PET, but an earlier version, which only had 2 rings. So I guess the take-home message here is that by optimizing both the image quality and accuracy, we can ensure consistency with systems that are going to be translating from the Ingenuity onto the new scanner. And we can fine-tune the scan parameters and or the reconstruction parameters in order to do that. So on to quality control. In order to have quantitative accuracy, you need to have a strong quality control program. So quality control is a series of tests that you do regularly to make sure that everything is working the way it should be. And the whole idea of having this program is that you want to identify problems before they have a chance to impact the patient studies. And you also need to bear in mind that once you set up one of these programs, you need to review it periodically and update it as experience teaches you that there may be other things required. So since we measure all the doses on a dose calibrator, it's important that we verify that that is operating correctly, The majority of these daily checks are done automatically by the system. And then on an annual basis, our friends from Radiation Safety come and do annual testing of accuracy, precision, and linearity. So we have a whole series of daily QC. This is performed by the technologists. And on the PET side, it does a full system initialization, which basically downloads fresh copies of the calibration tables onto the scanner. And that helps us ensure that the tables haven't gotten corrupted over time. We have a baseline collection which looks at the analog offsets of all those photomultiplier tubes and compares it to the previous day to make sure that there haven't been any large changes. And both of those can be done without activity in the field of view, so you can schedule it for happening before the technologist even shows up. Then the technologist shows up and puts a line source of activity in the field of view, and then we can measure the energy. We can make sure that the energy peaks are centered around 511 keV. We actually, in order to do time of flight measurements, we have to do a gain calibration every day because it's so dependent upon the PMT gain. So we actually, as part of daily QC, do a calibration every day. Then afterwards, we do an emission collection that we look at the sinogram of it and look for gaps that might indicate we have line of response missing from the data because of detector problems. We also measure the timing resolution, and we've actually added another test which experience has shown us is necessary, which is one of the problems we have. We have PET QC and we have CT QC. We actually learned that both of those could pass, but you couldn't actually do PET CT scanning because they're two separate systems. So we added in a scan which would then guarantee by doing a PET CT scan that the systems were communicating with each other and that they both agreed on where events are positioned. So in the interest of time, so this is how we do it. We just put a point source of activity in and to the scanner, and we do a PET CT of it, and then we look at the result and make sure that when we overlay the CT, that both of them agree that they're in the right place. And the fact that we have a reconstruction to look at means that the CT and the PET computer systems are talking to each other. On the CT side, we put the manufacturer's Phantom in there after warming up the CT tube to its operating system, and we scan a water layer in what they consider the head section and another in the body part of the Phantom. That's why it has two different sizes. It's to simulate both brain and body. And then we look at those, put areas of analysis on them and compare. So from this simple comparison, we can look at image noise, we can look at uniformity, we can look for artifacts, and we can also make sure that the CT numbers, the Hounsfield units, are correct for water, nylon, and these Teflon pins. So all the QC from now on is performed in most places by us, the physicists, as opposed to the technologists. So on a monthly basis, we do these checks. We want to look at the uniformity and the accuracy of our SUVs. So we can do that by scanning a uniform cylinder. And I'll show you what that looks like in just a minute. We also do, as we are credentialed by the American College of Radiology, as part of that, in order to maintain our certification, they require that we scan a Phantom on a quarterly basis, which provides us with information about contrast recovery and spatial resolution. And then on the monthly side, we do constancy, and we scan a different part of that Phantom. So for the uniform cylinder, we have this 30 centimeter long cylinder, 20 centimeter in diameter. We put activity into it so that it's in the range of concentration that we would see in a patient, and importantly, we scan and reconstruct it using the patient protocol. And then we get a result which looks like this. So we have a nice uniform image that was generated from our uniform object. And by superimposing the PET and the CT, we can also get a check to make sure that the PET and the CT are aligned. But then we also do a quantitative analysis. So we put a region around the cylinder, each axial slice of the cylinder, and we look at the average SUV in that region, and we plot it from one end of the cylinder to the other. And the value that we want, as I had mentioned before, is 1.0. But the value that we will accept as being good enough is a value between 0.90 up to 1.10. We can track this over time. The other thing that we expect to see is that there shouldn't be a change from one end of the cylinder to the other. In other words, that the axial variance shouldn't change by very much, and our pass-fail for that is 10%. So just to show you some examples, not from our scanners, but from cylinders which were submitted to the American College of Radiology Imaging Network for qualification of scanners, these are less than ideal uniform cylinders. We have ones where we have a big dip in the center, which could indicate that their scatter correction isn't very good. Even though the average SUV is in the right range, 0.99, practically exactly 1.00, we have this axial variation. And then we have something like this, where there's this constant variation from one end to the other, which could be because when they added the activity, they didn't mix it, so that there actually is higher concentration at one end of the cylinder than the other. But it also could indicate that there's a bad normalization, so that this scanner needs to be recalibrated. And on a quarterly basis, we do this ACR PET Phantom. This is a larger version of the one that I showed you before, so it's 20 centimeters across. It has these fillable cylinders with sizes that are listed up here. And then we also have a cylinder with no activity. It has water but nothing in it. It has air, and it has Teflon, which is supposed to be a bone analog, so that you can also test not only your contrast recovery for different sizes, but also the accuracy of your attenuation and scatter correction. So this is one of those scans, a slice through those cylinders. You see here on the right the PET, and then superimposed with the CT. So you fill this according to how much you inject into your patients. So you want to approximate the concentration that you would have when you scan a 70 kilogram patient with whatever activity you inject at your institution. And if you follow the formula, then you'll end up with an activity concentration between the hot and the warm background of 2.5 to 1. So then you analyze your image by putting regions, and you check these values, basically. So ACR says that this phantom will pass if the average of the SUV in the background falls in. You can see this is a wider range than we use for Akron. They actually go down to 0.85, where we stop at 0.90, and they go above by the same amount. So they accept 0.15, in Akron, that's 1.1 as the top. And then they look at the max SUV in the largest of these cylinders, and they want that value to fall in this range. Then they look at the difference between the next largest and the largest, and they want that ratio to be above 0.7. So for this particular scan on our Ingenuity, wow, we hit the mean SUV right on the head, and we have very good numbers for the rest of this. So we would say, good, we're done for this quarter. We'll worry about that in the next quarter. And as I mentioned, for monthly CT, we scan through a different part of this Phantom, and it has a lot of more materials. So it has pins of a lot of different materials that we now can check to make sure that our Hounsfield units are correct. And so we're given a range of what is the correct number, or the range of acceptable values. We also, in the same phantom, can get a feel for low contrast. So there's these low contrast pins, deliberately difficult to see. So you have to squint to the hard. We've discovered that the more time that you have your phantom, that actually CTing this phantom over time makes them even lower contrast. So it becomes quite challenging to see them. And the other information you can get is you know that the physical dimension of this pin down here is 50 millimeters. So we can check to see that this is what our system is telling us. And we also can look for the smallest, we should be able to see this, even the smallest number, the smallest of these holes. So that's an indication of resolution. So I see that we've run out of time. So I will just tell you that there's additional information that's in here and mention one additional thing, and that is when we go to look at doing quality control on these long axial field of view scanners like our PET Explorer, the question is going to be, how do we scale up to the measurements that we make on our current systems to account for a system which is much longer? So this is an example of how one group chose to do it. You say, okay, well, we'll just take our existing uniformity phantom and we'll put 5 of them together so that it's long enough to serve as our uniform phantom. And for our NEMA measurement, where we're doing that scatter measurement, we'll just add 3 of those up so that it's long enough. So as we build more rings onto the PET Explorer, we're going to have to investigate what the optimum way of measuring and maintaining measurements of how well the system is performing. And that's part of the ramp up of having this new piece of equipment. But in the end, once we understand what we need to do, we'll be able to incorporate the information, we'll get the corrections right, and we'll be able to make sure that we maintain quantitative accuracy with our previous generations of cameras as well. So I'll just stop by thanking both Josh and Joel for contributing slides to this presentation. Are there any questions?
It's quite heroic, Jen, everything that you go through just in order to have data that are reliable and quantitative and that can work even within one system, much less going across systems. Do other places have similarly rigorous protocols, and how did that evolve, and what happens if someone doesn't have as rigorous a protocol but wants to be part of a multi-site PET project? How does all that work out?
Well, yes. Okay. It works out. As I mentioned, we're involved in qualifying cameras for participation in the ACRM trials, and so we get. I see hundreds and hundreds of cylinders that have been measured on all of these different systems, and It is indeed scary to see what is going on at some sites because they don't have people who understand the system well enough. There are many sites where they don't even have a physicist in nuclear medicine. They have somebody who comes in, they hire somebody, a physicist, to come in once a year and basically sign off that the system is good enough. But from day to day or week or month, they don't have any indication of how systems are going other than the manufacturer's daily QC, which will throw a flag if something major is wrong.
Wow.
But yeah, so this is why if you're going to do a multi-center trial, it's so important to do some sort of check before you accept data from a system that you can believe.
It also points to source of variability that's in the literature that's just in there, even with people doing their best with what they've got at their site. But if they don't really have the extraordinary kinds of checks that you do, and the checks and rechecks again, things can go awry. you know, and something might not replicate. I mean, is what it would really come down to.
Right.
Yeah, I think that's a really good point, Rose. This is Jake. I think if you don't have a good consistent sensitivity in your system, you're going to not see your hypothesized difference using the N that you've planned for, which is going to be very problematic in designing a prospective experiment. From my experience as a clinician, we look at studies from all around, and it's just such a pleasure having the confidence and knowing that Janet and Joel and Josh and the whole team put so much effort into our instrumentation here that we have a lot of confidence in it, knowing that they're doing a very thorough job with all their testing across all our clinical sites.
Absolutely.
I was wondering, and Janet and Joel, this is more to Joel, but with these Phantom studies, there's this proof that we're looking at individual how good the Explorer is at individual organs compared to the standard clinical instruments. And so, I've been trying to think hard about how we can use it for really exquisite brain images, thinking about, the center of the bore, which is the sweet spot here in the machine versus the end. Are there any other studies that you've been thinking about or other people have been thinking about that you think could really accentuate how powerful and sensitive this instrument is for the type of neuroscience studies we're thinking about doing on it?
Well, let me take a stab at that, Jake. I think that what Janet described are the let's call it the most basic and generic tests that have become standardized, particularly with the ACR Phantom, and obviously the NEMA, which is more basic performance. But I think what's important is as we get to studies that are of more interest to you and the others, then we have opportunities to fine tune our measurements. And in the past we've used a Phantom. It's referred to as the Alderson Phantom that has regions that are meant to mimic the regions that take up the dopamine or the striatum. And there are others that we can do like that are much more specific to the task at hand. And that's always the key word. Let's do a study or a Phantom measurement that is very task specific. So we know what the basic performance differences are. We have better spatial resolution and much higher sensitivity. But in order to see how that's going to translate towards the type of study and allow you to plan the power of the study and so forth, we'd be happy, because I think this is quite interesting, is to figure out very specific set of measurements that we can do to explore that beforehand to help you plan it. And some of that has to do with what you've said before, whether or not there's an effective trade-off where the resolution is going to be slightly better if you're at the very edge, but you're giving up the sensitivity. With the longer bore, which is the way that it's now positioned in Stemler, I believe that we're going to have the best of both worlds, that you're going to be able to get both very good spatial resolution and high sensitivity by not being as restrictive in the 3 rings. So have a little bit more luxury to do that, which is nice that we have it. I'm not saying that everybody can do the same. But again, I think we should all sit down together, and you start by telling us what you think is most relevant for your studies. And Anna Rose and others, the same thing is that we fine tune the measurements to your protocol.
Yeah, that'd be great. The other opportunity in terms of cross-calibrating the system for brain would be with Yale and P30, where Rich and his team have that HRRT instrument up there with really exquisite spatial resolution in that. Yep. Just for the neuro more psychiatry leaning people here a couple of years ago, I think it was 2013, they actually used a tracer and were able to find a signal. I think they were looking at PTSD in the locus ceruleus, which is a very small piece of neuroanatomical kind of tissue. So to be able to get something that's so small and feel confident that they're getting a signal out of that, and be able to compare across sites, I think is a unique opportunity. But we just have to pick the right scenario, as you said, to kind of really tease that out. But I think working with Rich and going back and forth, there may be
Okay.
another opportunity there. So
Yep.
I don't know what the project is, but I think there's something very interesting we could do in terms of pushing the system as hard as we can.
Yeah, yeah. And Jake, of course we would welcome to start these discussions sooner than later. We're in a way we have I mean, I know your time is split. You also have to cover clinical duties, but and it's not as if we're sitting around with nothing to do, but I think this is nice for us to be able to sit back and make these plans before we're ready to go forward with a new scanner. And these, obviously a lot to do with the P30 project is a good time for us to think about this over the next few years, how to plan it now. So again, I'm happy to have those discussions whenever you're ready.
Yeah, thanks. We're getting there. I get a few more protocols rolling, but we're getting there.
Yeah. Okay. Good.
But we are so grateful to have the sophistication of Janet, Joel. The team is just it's remarkable, and there is so much to be checked and to be quantified and to be calibrated. It's extraordinary when we do replicate within a patient twice the same thing, even within a patient within the same platform. And of course, to say nothing of the inherent variability from patient to patient, even within conditions where we're, wishing for some homogeneity, there's a lot of heterogeneity. So the more error that we can remove at the level of, obviously, the scanning and acquisition, the better we are close to getting a picture of the truths when it comes to individual heterogeneity, rather than just being measurement noise.
Right.
So very grateful.
Good.
And test retest is a very important thing.
Yep.
For a lot of these studies. So we I don't know if you were trying to build that in too with some of our studies. I haven't been thinking as rigorously about it, but maybe that's a direction we should be going with this instrument from a neuroscience perspective, the test retest.
Well, thank you guys so
Janet
very much.
and Joel. Hi, this is Teresa. I just had a quick question. Are there any hormones, enzymes, amino acids, et cetera, that are not conducive to this kind of study? Or can anything be used for this particular kind of study?
You mean, do we have a tracer for everything?
Yeah, well, in essence, is it possible to make a tracer for anything, or are there any things that cannot be done with this kind of study?
Is Bob Mack on the call? I don't know. I think that basically almost every tracer that we make new has a trajectory to it. There are several, though, that are existing tracers that are available, some that are being used here or that could be brought here from other protocols that have been developed elsewhere. But I guess if you have a specific question about a specific kind of receptor or specific kind of metabolism measure, basically bring it as a question, and basically we'll see if something's already been done or if it's something that, would be relevant, especially to the P30, where there's this mandate for looking to things, that we could develop if they were relevant, especially for opioid use disorder, but obviously more broadly.
Right.
Everything takes time if it's a new tracer.
Yeah.
If it has to be brought all the way from animals to humans, that's a multi-year trajectory usually. But there are several tracers, many different kinds of transmitters and processes that are already available, including neuroinflammation, the various opioid receptors that we've talked about, tracers for transmission elements of the dopamine system, and on and on and on. There are just many, many, many. So if you have a specific interest, please email us and we'll get to
Yeah,
it.
the particular thing that I was interested in was cortisol.
So
That's a reliable molecule. That's very tough to do. There's a lot of interest in it because it has broad applications, but it's very, very hard to measure. Someone was going to comment on it. I'm sorry.
Yeah, no, it's me. I mean, what aspect of cortisol are you trying to measure? I mean, you can measure cortisol levels in plasma very easily, but are you talking about imaging the glucocorticoid receptors, or?
I'm not as sophisticated as you guys. I just was interested in, and this could be an offline discussion, but just interested in the implications of cortisol and different, the impact on different systems, I guess.
Well, cortisol is usually used as a stress response, right? You usually measure cortisol to look for as a marker.
Right.
Well, thanks for indulging the question.
Hi, Janet.
Yes.
Hi, this is Zainab. Would you mind if you send me your slides so I can put it in the PenPaste website?
Sure. Happy to do it.
So much.
Yeah, we'll pop them on the psychiatry website too if you just want to give them to Chris Petro. So it's a good thing to have in two places. Not everybody will know to search the P30,
Yeah.
but so.
Yeah. Hi, I'm back. I'm sorry. I keep cutting out whenever I try to speak. I mean, what I was saying is cortisol is usually used as a stress a measure of stress, right?
Yes, yes.
So how the things typically do is one looks at other transmitter systems that could respond or adapt in response to stress, and then try to relate what's going on in those transmitter systems to cortisol levels. That's one way it's been done in the past. Okay.
If at all possible, if I could find an article or something that you could refer me to, that would be awesome.
Okay.
I can send you some things. We can send you some things on
Yeah.
cortisol and stress response and paradigms that have been used to study that. For example, with fMRI, as Bob Mack says, I don't think it's labeled as a as a tracer, but there are things that you could use as correlates, and that you could probably make a case for looking at the relationship between your cortisol levels in blood or plasma, and then basically go from there with a receptor system in the brain. For example, there's seems to be cross sensitization with the stress system and the dopamine reward system, and so we could talk a little bit more about what you have specifically in mind.
Okay,
That would
thank
be
you.
helpful.
Okay. Anyone else? All right. Well,
Okay,
I
great.
thank you for your attention.
Thanks so
No,
much,
thank you,
Janet. We
Janet.
really appreciate it. All right, and we'll hope to see everyone next week. We have a different speaker, Emma Johnson, but we'll send out the notice. Thanks a lot.
That was great, Janet. Thank you.
You're welcome. Bye now.
Thank you.